pressure's on for the rest of you. So Peter's been an MQ senior scientist since 2003. From 2010 to 2017, he was the head of the boundary layer turbulence section, BLT. And since 2013, he's been the head of the geophysical turbulence program. Peter has participated in and planned campaigns, horizontal array turbulence study, HATS. Then they did an ocean version, called ocean horizontal array turbulence study, OHATS. I was sort of a nod to the Irish background. The name is OHATS.
Oh, very good.
Canopy, same thing, chats. Great acronyms. Focused on the measurement of subgrid scale variables in the atmosphere. Peter's research interests are in simulations and measurements of turbulence in geophysical settings, subgrid scale modeling, air-sea interaction, effects of surface gravity and water waves, surface gravity waves on marine boundary layers, impacts of stratification, turbulent flow over hills, numerical methods. Peter uses large eddy and direct numerical simulations to investigate turbulent processes in both the atmospheric boundary layer and the ocean mix layer. And today is going to be a combo here. The large eddy simulations of the wavy over the wavy upper ocean with submesoscale surface heterogeneity. And Peter, to you.
Sorry for the flounder. We'll make do. This is not a regular MQ topic by any stretch of the imagination, so I thought I would give just a tiny bit of background how it started when I first came to NCAR. Jim O'Malley and Jim McWilliams, they said, hey, we can get money from ONR to look at coherent structures in the atmosphere and the water. And of course, Jim being the water guy, we need LES of the upper ocean. At that time, LES in the atmosphere was being practiced, but the oceanographers really hadn't adopted the technique yet. And so we turned the code upside down, essentially, and started doing it. And since then, it's been a continuous stream of funding. Just as a bit of background, the talk is about a third sort of getting comfortable with this notion, and then the real thing will start. Start with some simple pictures at first. We're going to talk about wave current interactions, okay? And so the poster child for this is Langmuir circulations, okay? Irving Langmuir floating across the Atlantic noticed that scum lines formed, and he pretty much had the idea already sussed that there must be these coherent rolls underneath the water that were rotating in the along flow direction, and they were driving surface material into lines. Okay, so in 1997, with Jim and Chen Ho, we wrote a paper, and Jim coined the term Langmuir turbulence. First time that it was, and since then the idea and the term have propagated everywhere. The next picture is a postdoc sent me this one. It's Langmuir circulations and high winds. This is the Ermiger Sea, okay, and you see rather spectacular steep waves, but you also still see the foam lines from the breakers, okay? This one is actually an animation. One of my friends at the German Weather Service passed it along. I haven't had a chance to play this one, but it was a Russian freighter going around the Drake Passage, and when it when they turned the camera to the front, there they are. You know, so you see the real thing. There's big breakers, long foam lines, really spectacular fluid mechanics. And the foam lines are pervasive, and the foam is actually in the water. Okay, so those are just some pictures of wave current interactions, Langmuir cells. This first bullet is usually the modeling of an ocean boundary layer. They treat it like a shear-driven layer, and it obeys law of the wall scaling, etc., with negligible wave influences. But if you actually think about coupling the atmosphere and the ocean at sort of the atomic scale, how it actually works, the fluxes actually pass through the wave field. Okay, the surface wave field, you saw breakers, they support wind stress, form drag associated with all the wave field. It breaks intermittently under high winds, and this we'll show this just in a minute. It's not obvious, but it also generates wave average currents. So then, at the sort of atomic level, do waves play a role in air-sea coupling, and do they alter the classical picture of how the ocean boundary layer works? And this is kind of a bold statement. Do climate models need to account for surface waves? Well, because of some of the things I'm going to show here, there is a fascination with including the surface wave field in a climate model. Okay, so we want to get after phased average wave current interactions, and so we're going to adopt Craik-Leibovich, Sidney Leibovich and Alexander Craik, along with Jim and others. They said, okay, how can we get rid of the waves but preserve their effect? And so they introduced this asymptotic expansion. Epsilon's the waves is AK, the wave slope. Okay, the assumption there is that the waves are going a lot faster than the currents develop. So there's this spatial separation between the currents and the wave field. The wave field is supposed to be short compared to the time scale for current development, and so the time averaging is over the fast wave motions. Well, lots of algebra. The critical result is we end up with regular Navier-Stokes, but you end up with this unusual term on the right-hand side, U-Stokes cross the vorticity, okay? Sidney Leibovich called those vortex forces. So we're going to use that kind of approximation, okay, but with the addition of U-Stokes cross omega on the right-hand side. Whoops. You can see that that might be important if you actually make the vorticity equation out of this. It's del cross stat. It ends up that it appears in the advection term, but also in the stretching and tilting term. There's the gradient of U-Stokes. So one of the things about the theory as it is, it's the effect of the currents on the waves. Excuse me, it's the effect of the waves on the currents. The feedback is ignored here. So U-Stokes is assumed to be given, much like geostrophic winds, etc. Okay, so it ends up that the formulation is really this hybrid Eulerian Lagrangian sort of way of looking at it. Okay, so Stokes-drift, I realize, is not right at your fingertips, so I thought I would just steal a little animation. I played this once before. Imagine, if you will, you have a wave field, there's no currents, you put a cork at the top of the water. If you wait over a period of time, the cork will end up, and the waves are propagating that way, it'll end up at that wall over there. The orbits of the particles are not closed. They decay with depth, okay? And if you average over all that, you end up with something that looks like this exponential. That's the Stokes-drift, there's Z. Okay, so it's the net effect of the waves on the currents. Okay, and so since this is a vector relationship, it factors into all three components. Okay, so in that 1997 paper, we learned a lot of things, follow-on pieces of work. Langmuir turbulence. It's the ocean boundary layer regime where the phased averaged wave current interactions are comparable to or greater than shear buoyancy. So if you imagine a map where normally you have a boundary layer that's shear and buoyancy driven, you put a vertical axis on it where the wave effect is then the third axis of that. What happens is it's non-local vertical transport. Because there's a persistent gradient of the Stokes-drift, it acts a bit like convection. We end up with near surface intensification of the span-wise and vertical velocity variances. Okay, so if the flow is going this way, W gets amplified, but also the span-wise component. In a large eddy simulation, it makes Langmuir cells. Okay, I'm not going to talk about it today, but the downwelling, it also makes downwelling jets when you actually have breakers at the same time. So the characteristic number is the turbulent Langmuir number. It's the square root of U star over U Stokes. So it ends up that most of the ocean is in LAT equals 0.3, which is definitely in the Langmuir regime. Okay, this is just one of the projects we had was to look at Langmuir cells as driven by hurricane winds and waves. This is just an example from a simulation driven by Hurricane Francis. It's the right-hand side of the storm where the winds and waves are really aligned. Okay, so you can actually see those are signatures. The blue are signatures of the Langmuir cells. Okay, and if we play it, that's what they look like decaying into the water. Okay, so they're depth filling. Okay, so these little small things turned out, they're small here, but they descend with depth. And they're definitely random, but organized. Okay, Eric DeSaro at University of Washington, he works in the Applied Physics Laboratory. Eric is a measurer, and he had the good sense to say, I don't believe this Langmuir stuff. Every time I measure something, the waves just proceed with the wind speed. And so after nearly a decade, he finally made this plot from one of his Lagrangian drifters. All the green circles are open ocean measurements of WRMS. This particular device can measure W, not moments of W. I asked Eric, can you measure W cubed, which would even be a stronger signal? He says, nope, can't go there, but I can measure that. And so the open ocean lines are this way. These red dots are from Lake Washington, where there was winds, but relatively small waves. And so it really does live outside. Okay. In the Langmuir regime, we end up with a different scaling of the turbulence moments. Okay, so if you have a usual flat wall boundary layer blowing this way with the winds aligned with X, you end up with U prime squared bigger than V prime squared, and then it's bigger than W squared. In the Langmuir regime, you end up with V prime squared and W squared are about the same size and much bigger than U squared. So it's definitely a regime all of its own. Okay, with that little bit of background, we're going to talk about submesoscale turbulence, how it impacts that regime. Okay, so a couple months ago, I showed these two upper panels. This is simulations from ROMS. Okay, so when ROMS has nested grid capability, much like WRF, okay, and they end up with, when at the finest mesh, they end up with long, skinny filaments. Here's another filament, beautiful pieces of art. And the ocean is just populated with that particular phenomena. This is a nice picture. It's actually a front. You can see that the water here is a different color than here. There's scum line. Maybe there's Langmuir cells there, and it's collapsing on itself. So the scales there go from 100 meters to 10 kilometers. That's sort of the sweet spot for submesoscale turbulence. But we want to be able to do that flow plus that flow, okay, where the vertical scales are boundary layer scales. And simple questions are, do they interact? Do they couple? Do interesting things happen? It's a science question. Okay, we need, Frontogenesis is a familiar atmospheric topic, but the oceanographers have fallen in love with the topic also. So I borrowed definition from Jim. Frontogenesis, it's the fluid dynamical processes that rapidly sharpen horizontal density gradients, okay? The secondary circulations accentuate the frontal sharpening until an arrest occurs. So that's the magic. What makes the arrest? Is it a frontal instability or some turbulent mechanism? So the picture here, there's a filament. It's cold and dense right there. There's the top of the water, okay? And so it's tapered so that it gradually goes to light fluid on the sides. So if you just tickle this right here, perhaps it'll sink and create this secondary circulation. Associated with the main filament are geostrophic jets on the side. Okay, so under what conditions does frontogenesis occur? What's the life cycle? What's the arrest mechanism? Okay, so there's instabilities, those kinds of fancy things. There's a lot of work in the oceanographic literature looking at these sorts of instability mechanisms as a way of halting the frontogenesis. But it often happens in the boundary layer. A lot of times the boundary layer is this deep, and so the front itself sits in the boundary layer. So can you get frontogenesis? Okay, in a boundary layer sort of setting? It ended up that Jonathan Gula in ROMS found it, okay? In the ocean boundary layer regime, it's especially through something called turbulent thermal wind. And so what's the role, if any, for turbulence and surface waves in this process? So we need a little definition of turbulent thermal wind. If you just put on your boundary layer hat, TTW is just a diagnostic way of looking at the flow. It's quasi-steady, linear momentum balance, combines these other things. For that particular flow, for a 2D filament, you end up with these two equations. That's the Coriolis force, there's the pressure gradient, written in terms of a buoyancy, and then there's turbulent fluxes. So if the turbulent fluxes disappeared, the geostrophic jets would just sit there, not do anything. But because it is turbulence, do we end up with coupling here? Okay? Is this divergence of this flux V prime is in the long filament direction. Is the divergence of that sufficient to drive a U, okay, and create this overturning circulation? Okay? So that led us to do lots of LES in a very big box. Number of points, 8192, 3072, 256, okay? The size of the box, it's 12 kilometers all the way across, 4.5 in Y, 250 meters deep, with this kind of spacing. We have 16 cases, different combinations of warm and cold, but also with winds in the north direction, northeast, east, southeast. The parameter variations are really large. These 16 cases live on different supercomputers in the United States. Some are on Cheyenne, some are on DoD machines. We've given those solutions to different investigators. These were costly simulations, and so the community wanted to take advantage of those. We wrote 2 JFM papers, and there's a third one that's being revised. So the question here then, this is just the top of the LES. It's warm water, cold, warm. Okay, so there's a geostrophic jet this way and another one on that side. The width of that, it decays exponentially, but it's about 4 kilometers. So if we tickle it, will this happen? You end up with a secondary circulation on each side, squeezing here. This gets to be 100 meters. Okay.
Peter, when you say tickle it, what do you mean?
Okay, so the initialization recipe is such that no filament. I start the boundary layer in this big box as a homogeneous case. I run it until the turbulence is fully developed. Okay, then I stop the solution. I take that volume. I then put in the filament. So it's got fully developed turbulence plus the filament at the same time. Okay, I run that for 1.8 hours till they get compatible with each other, holding them constant, and then it's just a rundown problem. Okay, so the tickling is turbulence.
What happens if you just let the turbulence develop?
It will depend on the strength of the front. Okay, you'll kind of see that in just a little bit.
Could you repeat the question for the home audience?
Oh, Chris asked, what would happen if we didn't go through this fancy initialization recipe and just had random noise with the actual filament? And my response was, it will depend on the strength of the filament. Okay, whether you get frontogenesis.
So it's negatively buoyant, the filament that you're putting in?
Yeah.
Okay, it'll
Yeah.
sink.
It could be, the forcing could be winds and waves, okay? Or it could be just cooling, or winds and waves at different directions. We have all those kinds of cases.
Okay,
But the filament is geostrophically balanced initially, yes?
Yep.
so it's not going to sink.
No, it sinks because there's Ekman convergence where there's a vortex.
No.
Yep. Okay, just to prove, or just to show that frontogenesis actually occurs, I'll show this little movie. These are the ISO temperature lines. So it's cold and dense right in here. Okay, this is with surface cooling only. So there's just 100 watts per square meter at the top. It's held constant. Okay, so we're going to look at the ageostrophic component. Okay, so the jets themselves are into the are out of the board on this side, into the board on that side. Okay, let's play it again, but stop it here and there. Okay?
Those are laterally average currents?
Yep. Okay, so sure enough, the turbulence was enough to create an ageostrophic U. It's going this way. The other one on the other side, because it's just the symmetry of the problem, drives it this way. So you notice the temperature contours are being squeezed, 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 squeezed. So even though they started out at this very broad level, at this particular time, 3.8 hours into the simulation, already you see the convergence. Okay, by the time it gets here, the actual distance where all the frontal dynamics happens is about 100 meters. So it's this neat problem where it's very large scale, squeeze down, and then something right here happens and it stops. Okay. All right. This is just a XY cross-section of the previous example, so just a plane at the top of the water. That's how it starts. It's upside down Rayleigh-Bernard convection. The blues are all, for the next few slides, I'm just going to talk about the case with surface cooling. There's no winds and waves yet. Okay. The blues are down and the reds are up. That's how it starts. And there's what it looks like at the time when the maximum frontogenesis happened. There's the actual front. Okay, there's this neat region in between. And here it's Rayleigh-Bernard looking flow far from it. Okay. Each panel is about a quarter of the size of the box. So you imagine that it's folded over and then folded over again. There's more grid points than pixels. Okay, so for a long time I didn't appreciate what happened right here, why this happened. The movie showed that there's lots of U going this way, but what happened there? So this is a time average. This is a space averaged visualization of that flow. It's W prime squared. Before, when I was doing it, I was always fascinated by this really strong downwelling and what was happening there. But here I've oversaturated this regime, okay, to show what happens in the far field. So this is if you will, a John and Chen Ho flow. It's a convective boundary layer. There's W squared. It's about 0.3 on that scale. Okay, but you saw the really strong overturning. There's stable restratification right there. If you use W squared, or the absence of W squared as the depth of the boundary layer, then it goes here. So you end up with both sort of physical processes. Really strong downwelling, okay, overturning circulation that makes it stably stratified and collapses to something like that. W prime squared over W star squared right here is 10 or bigger. So like, to put that in perspective, if it was the atmospheric boundary layer, that ratio would be 0.3. Okay, so it's 30 times more. That's the strong front. There's a weak front. Same kind of phenomena happens. Okay, so what stops it? Okay, that was the holy grail kind of question. What are we actually resolving the fluid mechanics that actually makes it stop? Okay, the movie that I showed is actually the life cycle of the frontogenetic filament. Okay, there was zero, then it grew, reached a peak, then this long decay afterwards. So right at that peak, what are the physical processes that stop it? Okay, so in the U equation, the angle brackets are along filament averages. Okay, here I should mention this is a special logarithmic scale because we know that it collapses. If I just showed on a linear scale, difficult to show all the processes. Okay, so here the red is U prime, U prime. Okay, down here in the V equation, it's U prime, V prime. Well, it's pretty obvious that the slope here is of a different sign than the slope there. Okay, so those are the arrest mechanisms. If we take the V equation and we average in depth, okay, the approximate balance is that. So, turbulence is beautiful. It does two things. It started the frontogenesis, but it also arrests the frontogenesis in this really cool way. In one case, it was the vertical fluxes. There, it's the horizontal fluxes, U prime, V prime. I mentioned to Rich before the talk, V prime is king. It's really large. Okay, so it spills over into that flux. Okay, these guys are, it's a hard average to get, but approximately that's the balance. So, we had a lot of talk about, in a hurricane boundary layer, what the TKE balance is. Here, we can do that in a simple way, since it's just X, Y, and Z. You have a nice physical interpretation. Again, the angle brackets are averages in the along filament direction, essentially Y. Okay, so the TKE balance, there's the horizontal advection, so normally that term would be 0. There's the turbulent transport, the U prime squared, the triple moments and the pressure are lumped together just for convenience. Now you end up with this really long, neat shear term. It's got this and this. It's got these horizontal production terms. There's buoyancy and dissipation. Okay? So, far, far, far from the front, this is the upside down of John and Chin Ho's problem. This is just built using the resolved fields. The green is the buoyancy. So if you flipped it up, this is about 0.2. That goes to 1. There's the dissipation. There's the transport. So the advection and the shear term are near 0. Okay? So now if we go sit right on top of the front, this is right at x equals 0. When we made the plot and Jim saw it, he says, I didn't realize it was so simple. Okay? The shear term kicks way up. It kicks way up because of this. I'll show in a second. Okay? That black line is the turbulent transport. It can't dissipate fast enough, so the triple moments move it away, and that's the main balance. Unexpected. Okay. Okay. Once again, this is same kind of plot, but over the whole box using this special logarithmic axis on the bottom. It's double logarithmic. There's the advection term, there's buoyancy. The yellow is positive, and so it actually ends up being a sink right in the center. There's the dissipation, there's the shear term, and then there's the turbulent moment terms. So right there, it's negative and wants to push it away. Okay. Okay, if we take, just to show you that, if we take that shear term and we tear it apart, we split it into these two, and then the rest, we'll call this horizontal, that vertical. Oops. Oops. Okay, there's the horizontal shear production. It's u prime squared du dx. Okay, and u prime v prime. They're really big. It's 500. Okay. There's the vertical production. And if with this, instead of a production, it's actually a destruction term, and it's caused by this right here. It's w squared d by dz of angle bracket w. One of the reviewers of the paper didn't like this. They wanted this to be biggest. Well, it's not biggest. The horizontal production is bigger. This goes up to a scale of 500. That's minus 100. Okay, so the same, the triple moment, I'm just showing it just to, so you get a little bit of a feel. So the horizontal component of it, it's got this big negative piece right there and there. Okay. Okay. We were talking about spectra, and I thought I would show a little something of just the spectral energy. Once again, it's averaged in Y. Okay, so the lines are more wiggly than usual. Okay, so it's the along front, Y direction. Here's the case with no filament at the top of the water. It's just homogeneous case in a really big box. There's kind of the break point between what you would call submesoscale and boundary layer scales. This is W. This is the three components of the energy. Okay? All right. So if we input a very weak front, it's this orange curve, it nearly lines up with the no filament case. Ran it for more than 100 hours, 100 physical hours. Quite a costly thing to do. Okay? There's what we call a weak front. It's about 10 times stronger than the very weak one. Okay, so right away what you notice is, wow, the v prime squared, u prime squared kicked way up. So it generated all this energy to the left in the submesoscale regime. And then there's nothing special about this point. It just runs right through it. There's the moderate front. There's the strong front. Okay, so they all do approximately the same thing. This is just V prime over U star. Okay, at the time of maximum frontogenesis, well, you can see these big pulses of reds and blues that boost all the energy in the strong front case. Okay, what about surface waves? We'll go kind of quick. In the Craig-Leibovich equations, you end up with, those are vortex force terms. Okay, there's a Lagrangian scalar term. But the thing to notice is this has got an angle bracket on it. Okay, in the no filament case, averaging this term disappears. It's, if you will, conservative. If we average over the whole box, that disappears. But because there's natural heterogeneity, there's a net zeta, a net vertical vorticity. Okay, so TTW with this, it's the same kind of thing. The hydrostatic balance, it looks like a buoyancy term. Then there's those vortex forces with angle brackets on them. Okay, so in the TTW way of looking at the momentum balance, okay, before when I showed it, it just had this term and this term and this term. but the waves added a whole bunch of extra things. This is a Stokes-Coriolis term. This one, it's dV Stokes with an angle bracket on the zeta. So I showed you zeta is, when it squeezes, it gets really big.
Peter, can I ask, so it's not in hydrostatic balance then?
This is hydrostatic balance.
But what about, you got velocity?
That's, yeah, there's no W squared in there.
Right, but I mean, the hydrostatic balance is by definition just dP dz is equal to buoyancy. That's it.
In the Craig-Leibovich equations, you get those extra terms. So the pi, that's why this isn't a p, it's a pi. Okay, there are several ways of writing the Craig-Leibovich equations. We use the vortex force term. You can make this be a regular p, and then those guys disappear and they get lumped into other terms. Okay? All right. So zeta's big. It might do something to this. Okay. So these are just simple time series plots. Here's zeta. So it's the vertical vorticity. So it's dV dx. Okay, as it squeezes, that divergence, that gradient is getting bigger and bigger and bigger. There reaches its peak, and then whoosh. So somewhere in there, this is where the peak in the Frontogenesis happens. This is a case with north winds. It ends up that that's the case that the oceanographers really like. Okay, here's the TKE that goes with it. It's normalized by U starred, so you can see how strong the filament makes the TK at the top of the water. Okay, so if we just simply take the winds and put them in the east direction, it's this yellow line. Okay. Okay, so yellow plus the bullet, it's the east wind plus waves. Okay, so the winds are blowing across the filament, and the waves are too. Okay, so not much change. North winds and waves, it knocked down the peak to this particular value. So what happened? Okay, this is how the temperature field looked like when I started. The jet on this side with winds blowing this way, it's positive, negative. At the peak of Frontogenesis, this is the case with no waves. You can see that really collapsed frontal zone. But when we added waves to it, we ended up with this tilted front, if you will, with spacing in between it. Okay, jets and no waves. Okay, there's a really strong jet on this side, negative this way. They're separated by some finite distance. When we looked at jets with waves, it took the jet and tilted it, okay, in this funny shape. And so we'll skip this point. And there's the front. It's a tilted front, if you will. Okay. Ned helped me make this movie. So imagine, if you will, we're at 10 meters into the water, and we have this magic camera that will sweep across the level at 10 meters. So this will move, okay? In the top, the red is vertical vorticity. The black is just the geostrophic component. And so we just want to watch what happens. So it's just the downwelling lines, okay? So these guys are the signatures of the Langmuir cells. The aspect ratio of the plot is 1, so we haven't cheated. If you watch close, all of a sudden the spacing gets smaller, the cells themselves get smaller, okay? Yeah, but it blows across. Oops. I'm sorry, messed it up. Okay. There's where the front is. It made the waves made the whole front relatively wide compared to the no wave case. There's what zeta does. There's the ageostrophic component. Okay. So once it goes through this frontal zone, then the waves reappear, then the Langmuir cells reappear. And then the whole process starts again. Okay, so here's just the vertical velocity, no waves. There's just this real strong downwelling jet right in the center. Okay, with waves. You can tell this is the with waves. All these little, this is averaged in Y. All these little patterns right here are signatures of the Langmuir cells. And then the whole width is a lot bigger, and it made this really interesting downwelling spot there along with that one. Okay, just quick, the direction of the waves matters. Okay, so the white is north winds plus waves, the yellow is the east, and these are the two intermediate cases. Okay, so just a quick summary. With surface cooling and a cold filament, the turbulence, like I said before, the turbulence starts it, U prime, W prime, V prime, W prime, but it also arrests it, the horizontal components. I've often interpreted this, Jim doesn't like this, it's like a Kelvin-Helmholtz flow turned on its side, but the edges of the KH driving mechanism are getting squeezed at the same time. In the TKE equation, at the place of maximum frontogenesis, the shear is approximately balanced by the turbulent transport. The Langmuir turbulence and the submesoscale filament, they're coupled, okay? They modify the hydrostatic balance. The waves themselves actually cause asymmetry in the flow patterns. If you were actually going to measure this, you need to include winds, waves, and the wave directions. I'll stop there. Thanks for your attention.
All right, questions, comments?
So, Peter, what would happen if you didn't have a filament, you just had a front?
A front?
What we would call a front.
Yeah. We've asked that question, and it's hard to make the code be periodic nicely. That's why the filament is, okay.
But you could take a wide filament, right?
Yeah. A single front, the frontogenetic life cycle would take longer, okay? It doesn't have the power of both sides squeezing, okay? So Jim showed with Greek symbols that the filament is actually, what's he call it, super exponential. It grows at a super exponential rate, whereas a front itself would just be exponential. Did this with KPP and those kinds of things.
Okay.
It's a good, Chris, it's a really good to-do problem.
I have another question, but somebody else can go. Go ahead. Okay, I have another question. So suppose we just were like 20 years ago and we could afford to run sort of a 2D simulation of this thing.
Yeah.
So we've removed all the variability that you're resolving with LES. And we would see this kind of convergence in the mean sense. And if we did something simple with some sort of eddy diffusion,
Yep.
there'd be a balance between that inward advection and the. So is that different than what you're finding, or is?
Yeah, because the eddy viscosity you would put in would be associated with something in the vertical.
Well, it would depend on how narrow that front was, right?
Okay, yeah. So it's the eddy viscosity in the horizontal direction that would stop it. The other one would just be, it would run until it got to that point and then stop itself.
I agree. That's what 2D simulations show.
Yep.
Thanks, Pete, for the talk. It's perhaps a stupid question. Are there effects of salinity here? There is temperature, but salinity, and there is always this interplay between both in the ocean, as far as I know.
Yep. So the code can have salinity. Okay, so essentially it's what I put in is the temperature compensated salinity. But salinity is really interesting because it creates all these special fronts, like in places like the Indian Ocean, so it decouples itself. So it's just another parameter variation.
Hey, really interesting stuff. What fundamentally determines the spacing of the Langmuir cells? Is it the length scale of the Stokes-drift term, the depth? You showed that drop. Is that pretty much the length scale that we're dealing with? Okay. Mm-hmm. And then do you have a relatively simple explanation for why that then changes when you have the frontogenesis? Because you showed the cells. I thought you were showing those getting smaller and smaller.
So the simple explanation is the winds and waves are becoming disoriented from the actual, the currents in the water are impacting the way that Stokes-drift works. Okay, it generates a large U in the water, and so there's misaligned winds and waves in the water. You wanted a simple reason.
So yeah, that last question in your intro, why are the climate people interested in this?
I'm sorry?
You had the question in your introduction. Why should this be of concern to the climate modelers?
Langmuir turbulence in general, because it causes more mixing, okay, than just a regular assumption of a U decaying profile. There's actually more mixing in a stratified regime. The Stokes-drift is independent of stratification, so it mixes more when it shouldn't, based on regular arguing, that kind of thing.
All right. Well, okay, Ned.
Thanks, Pete. That was great. So you showed cases with and without waves?
Yeah.
And showed that with waves, the vorticity dropped dramatically. So does that mean, in the fact that it's rare that you would have winds and no waves, that effect actually means that it goes away as an important piece of the puzzle? Or is that a misinterpretation?
You have to remember it's a LES parameter variation. So the case with just winds alone likely exaggerates the effect. Okay, whereas winds plus waves, there were still large horizontal gradients. It's just they weren't as big as the case with no waves.
Okay, I think we're at the end of our hour. Thanks again, Peter.
Yeah.
And please join us for some cookies, coffee, and chit-chat.
Hey, thanks for your attention, guys.